The purpose of this project was to create a piece of test equipment that was able to measure handle pull efforts and output travel. This equipment had to be able to accommodate all types of handle movements and output types, allowing for it to be universal for current and future Magna handle programs. Magna's current setup requires the handle to be mounted to a table where an instrument is then used to pull the handle vertically while measuring handle efforts and core travel. Because of the nature of this test, the placement of the handle is different every time, causing variability in the measurements. Additionally, the desired travel is the output travel of the handle, as this controls the latch of the vehicle. However, this is not possible to measure on the current instrument setup. With this knowledge, the senior project team worked with Magna to create a list of specifications that needed to be met for this project, which included a stability test of 300 newtons, a sound test of 85 decibels, a minimum travel requirement of 30 millimeters, a minimum effort requirement of 100 newtons, a gauge R&R to test repeatability, multiple time tests, data output requirements, power requirements, height and weight requirements, durability requirements, safety requirements, a budget of $5,000, and movement requirements. To reduce Magna's fixture costs, the tester was made to accept the same holes as another piece of equipment, so one plate could be made for both testers. A dimension box was made for the size requirements to ensure the tester could be moved to any location Magna desired. With these specifications laid out, the team began creating concepts that would eventually be evaluated using a weighted decision matrix. Once the design was agreed upon, the team began designing and modeling the tester in SolidWorks and creating prints for components. Along the way, different prototyping was done using 3D printed parts, as well as analysis was done by performing FEA and hand calculation on components. Once the design was agreed upon and the detailed design document was done, the team began ordering components. The first to show up was the 80/20 aluminum extrusion, ABS tabletops, and galvanized steel tabletops. With these materials, the frame of the tester was constructed, followed by the walls and top surfaces of the tester. The biggest issue with this was the warping seen in the middle of the table, which was later combated with additional supports and bracing. In order to test all types of handle movements in Magna's portfolio, 5 degrees of freedom were needed. The linear slide table provided 250 millimeters of y-axis travel, while the optical lift table provided 60 millimeters of z-axis travel. The last translational degree of freedom was provided by the linear actuator, which had a stroke length of approximately 100 millimeters. The 2 rotational degrees of freedom came from the rotary table, which provided 90 degrees of rotation about the y and 360 degrees of rotation about the z. The translational degrees of freedom and rotational degrees of freedom were kept separate to eliminate any complex geometries. While some of the team worked on building the table, other parts of the team worked on prototyping some designs that had been drawn up for the detailed design document. This end-of-arm hook design will be used to pull tailgate handles. One pin can be pulled to allow the hook to pivot downward, while the second one can also be pulled to allow the entire hook to completely drop out. To help with the budget, the team designed a linear encoder from a rotary encoder using a rack and pinion design. This allowed for the output cable of a handle to be measured using this rotary encoder. To run the initial tests, some prototype wiring was done to allow for the unit to be powered up. The team then designed a PCB to be ordered to clean up all the wiring and to reduce the chances of any wires coming loose during testing. Once the PCB board was received, the breadboard was swapped out to make the wiring neater. This is the final setup of the tester with the handle mounted to the fixture. To start the test, the travel and efforts must first be zeroed out. Then, selecting Start will run the program until one of the force conditions are met. In this case, 100 newtons was exceeded, so the test was stopped. After the test is completed, a travel versus effort graph will appear on the screen. This particular graph had 79 points, while the minimum required is 50 points. The travel for this test was 17.22 millimeters, while the total force was 42.98 newtons. Here, the handle can be seen attached to the fixture using thumb screws, which makes it easier and faster for lab techs to assemble and disassemble. Next, the Z and Y axis were adjusted according to customer spec before the handle was pulled by the linear actuator to full travel. As mentioned earlier, the team made a linear encoder out of a rotary encoder using a rack and pinion design. Here the cable can be seen being pulled by the door handle while it pulls the rack and moves the encoder. A torsional spring was added to create some back force to remove any slack from the cable before testing occurred. For handles that use a lock rod instead of a cable, a universal cable had to be made that would allow the linear travel of the counterweight to be picked up. Here you can see how this works on one of our handles. A lock rod is normally used for a push motion. However, the team was able to create a design to come from above, converting this linear travel into a pull motion. This pulls on a cable that is then routed back to the encoder to get the total travel of the counterweight. This 3D printed cable holder and guide is attached to a carriage that allows the system to move as needed for different counterweights. Here, sound testing can be seen taking place 5 feet away. At this distance, the peak sound recorded was 54.9 decibels, which was well below the 85 decibels spec'd out. Here, stability testing can be seen taking place. For this test, the table was pushed on from both sides with a force gauge at 300 newtons to ensure that no tipping or movement of the table occurred while the test took place. A gauge R&R was done to prove the reliability and repeatability of our tester. Our percent GRR that was targeted was 10%, and for the efforts we had 6.76, while the travel resulted in a GRR of 5.61. To perform these tests, 8 different handles were tested by 3 different users to determine how repeatable the setup was of our tester. Starting a test from scratch, the cable is first fed behind the fixture. The handle is then bolted down to the fixture using thumb screws. The cable is then connected to the rack. Then, by pulling on the housing, the slack is removed from the cable before being clamped down. The actuator is then jogged forward until a pin can be dropped through to grip the handle. The pin should drop freely, applying no preload to the handle. The Z-axis height can then be adjusted to the appropriate height, depending on the width of the handle. The Y-axis can also be adjusted closer to or farther away from the pivot, depending on customer spec. The table is then clamped down so there's no movement during testing. The travel is then zeroed as well as the force reading, and then the test is started. A graph is finally displayed to the user to analyze. One of the biggest issues the team had was running the gauge R&R. The first test yielded greater than 10% GRR. The main reason for that was the warping in the table from both the linear slide table and by the rotary table. To combat this, additional supports were added to stiffen up the table and eliminate this problem. Finally, having this additional support that touched off the bottom shelf eliminated any concern with having the table droop in the middle as we saw with our preliminary builds. The resulting final tester that was submitted to Magna can be seen in this photo.